Hello everyone. Galileo Galilei discovered the falling speed is independent of the mass of an object. But in our daily life, we experience feather drop more slowly than the rock. Then we need to include fluid resistance to explain the difference of the falling speed of a feather and a rock. I'd like to explain the fluid resistance. The really simple expression to describe the fluid resistance discovered by the Stokes. But this law is applied when the falling speed of an object is really slow velocity. Force is proportional to the v, velocity of an object. Fluid resistance always opposite directions with respect to the velocities. If the particle is moving to this direction, fluid resistance has the opposite directions with respect to the velocities. You have to put a negative sign. So K is a positive quantity, positive parameters. Then we'd like to introduce this effect to study the falling object. We'd like to write down the equation of motions. This is ma equal F. For the F, now we consider the x is a positive direction in the upward. So gravity is directed downward direction, so you should put a negative sign. Minus mg is a gravitational force. And gas drag force, I have explained the last slide. F equal minus kV. So we add the terms fluid resistance. Then these equations can be expressed by divided by the m, the both sides. So we have this equation. This is a differential equation that we'd like to solve. Then to solve this differential equation, it's better to change the variables. So instead of the lower case of the v, we use a capital V. So this quantity is expressed as v. Then actually the mg over k is a constant value. So if you consider derivative of capital V with respect to t, this is equal to the derivative of the lower case of the v with respect to t. Then you can substitute this relation to the left hand side and the right hand side. This equation substitute here. Then you will get this equation. So this equation is very easy to be solved. To solve this equation, we can apply the separation of variables. So dv over v equal minus k over m dt. Integrate. So this term becomes log v equal minus k over mt plus integration constant. So v equal exponential c exponential minus k over mt. So this part we change the variables v sub 0. Then you will get this equation. Then originally v is expressed, capital V is lowercase of the v plus mg over k. So you can substitute here. Then equations, solutions is expressed this equation. The v equal minus mg over k plus v sub 0 exponential minus k over mt. Then if we consider, if you drop the ball at x equals 0, for example, this is x equals 0, and then if you drop a ball, initial t equals 0, v equals 0. Then you can use this expression, these initial conditions. Then 0 equal minus mg over k plus v0 exponential minus k over m times 0. So this becomes 0. So this means exponential 0 means this is 1. So v sub 0 is mg over k. And substitute. Here this is a v sub 0. So we have this expression. that the t equal go to the infinities. What's happen? T equal go to the infinities. Exponential minus k over mt is approaching to the 0. So the second term is vanishing. So only the first term is we have for the velocity. V equal minus mg over k. We call this is terminal velocities. Falling velocities approach to a constant value of the terminal velocity. So if you draw the velocities, the vertical lines, horizontal line is a time, and then terminal velocity is minus mg over k. So if you drop a ball, it's approaching to the terminal velocity. So in this case, it's you just drop a ball with a velocity of 0, and it's going to down, and then it's reaches the terminal velocities. Sometimes you throw a ball upward. In this case, the starting velocity is some positive values, but even in this case, it's approaching to the terminal velocity. Sometimes you want to throw the ball very strongly downward. Then the initial velocity is a really negative value, but still it's losing the velocities. It's approaching to terminal velocity. Okay, this is the terminal velocities we studied. Then we'd like to apply Newton's laws to the dynamics of the circular motion of an object. So particle moving in a circular path with a constant speed. In this case, acceleration is expressed, the radius of the circle is a capital R, and the velocity v squared. V squared over R is the acceleration. Then second law is expressed, mass times acceleration is becomes, in this case, is string is attached to the object or the particle, and the particle making a circular motion. So this is tension force. Then we can apply the motion of the moons. The moon is making a circular motion around the Earth because of the universal law of gravitation. Gravity is acting between the two objects. Okay, and then we can apply mass m, lowercase of the m is the mass of the moons, and the acceleration, this is acceleration, ma, and this is the universal of gravitation, gravity. G times mass of the Earth and the mass of the moons, and the R is the distance between the Earth and the moons. Then from this equation you can solve the V. V is the square root, G m over R. M is the mass of the Earth. Then we can find out the period. Substitute. This period is a Vt times the 2 pi r. 2 pi r is the circumference of the orbit, circular orbit of the moons. So this is 2 pi r. So 2 pi r divided by the speed, rotational speed of the moons. Then you can find the period. Substitute. This b is here. Then it becomes a t period is proportional to the distance between the two objects. Okay, so actually this is corresponds to the Kepler's laws, third laws. So Kepler's law said planets move in an ellipse with the sun at one focus. The second law is a radius vector from the sun to a planet sweeps out equal areas in the equal period of times. So that this object is moving to this position. So for example, in a month, then also that this object is moving to a new position in a month. Then if you compare these two areas, it should be the same. This is the Kepler's second law. And the Kepler's third law said the square of the orbital period t of the planet is proportional to the cube of the same major axis of the planet. Kepler's third law, actually this equation exactly equal to the Kepler's third law. If we use Newton's second law, we can explain the Kepler's third law. Then we'd like to apply the universal law of gravitation and the Newton's second law to the motion of the other object. Edmond Halley applied the universal law of gravitation to predict the motion of the comet and confirm the validity of the universal law of gravitation. 1758. Safely applied the universal law of gravitation to predict the motion of the object in the solar system. The next question is that does the universal law of gravitation works everywhere in the universe? Then we apply the universal law of gravitation to describe the motion of stars in the binary star system to demonstrate the validity of the universal law of gravitation. Our sun is a single star, but half of our stars in the universe belong to the binary system. Actually, Sirius, the brightest stars in the night sky, is a Sirius. Sirius has a company. Actually, Sirius is one of the binary star systems. So Sirius A and Sirius B is circulating around their center of mass. So in this case, we consider that Sirius A is located at the focus of the orbit of the Sirius B. Sirius B is rotating around the Sirius A. And actually, we found that the orbit of the Sirius B is elliptical and confirmed that the universal law of gravitation works well even outside of the solar system. And we discovered the universal law of gravitation and the Newton's second law works everywhere in the universe. Okay, this is the end of this session.